Hello everybody, welcome to 8-1, solving trigonometric equations using inverses. Alright, so let's go ahead and jump into this. Alright, our learning objectives for today are first we're going to define and evaluate what an inverse trigonometric function is. Right, we're going to be able to use inverse trigonometric functions to find specific values for our angles. And then we're going to solve equations using inverse trig functions. So we're actually going to do a little bit of algebra to rearrange our functions so we can actually solve for things a little bit more complicated than just one single thing. All right, so first of all, what is an inverse trig function? So when we use an inverse trig function, we're finding angle measures. So if they're giving us this, let's say they give us this equation here where it says sine of theta equals 3/5. Well, first of all, what does that mean? Well, if we know that sine equals 3/5, we know sine is opposite over hypotenuse. So if we were to create a little triangle and we're looking for the sine of theta, we'd be looking at 3/5, right? Opposite over hypotenuse. We know that this is 4, just based on the Pythagorean theorem. It's a 3, 4, 5 triangle. It's a pretty common thing here. If you want to do the Pythagorean theorem to find that this is 4, you can, or you can just trust me. So if we have this triangle here, if we're saying the sine of theta, then we're referring to 3/5, right? But in order to find out what this degree measure is, we have to find the inverse sine. It looks like this, right? And the way that we do that is, well, if we have the sine of theta, in order to get theta by itself, we take the inverse of sine. So the inverse sine of 3/5 is going to equal theta, which in this case is 0.64 radians or 36.8 degrees, right? In fact, if you put that into your calculator, inverse sine of 3/5, inverse sine of 3 divided by 5, just to show you how I got this, we get 36.8, which is what I told you it was going to equal here, right? Whoops. Right? It's going to equal this. Right? Now, if we want to look at the other trigonometric ratios, we have cosine, which would in this case be 4/5, right? Adjacent over hypotenuse. And you'll notice that the angle isn't going to change, right? This is the angle that we're going to be using the whole time. So if we use sine, the inverse sine of 3/5, it's the same as the inverse cosine of 4/5, right? Which is the same as the inverse tan of 3/4, right? Opposite over adjacent. And they're all going to give us the same answer because that's what the inverse evaluates, is what is the angle, right? So when we do all of this, we're actually trying to find what this angle measure is. Okay. So now we're going to get to a topic that's a little bit complicated, okay? So let's look at sine and inverse sine here for a second. And let's just look at it on a graph, all right? So let's look at sine, right? We know what sine graph looks like. Now let's look at inverse sine just for a second. And you'll notice that it's tiny, right? And why is it so small, right? That seems weird. You'd think that if we have a graph that reflects over the line y equals x, right? I'll just post y equals x real quick just to show you. So if we are going over this line, right, you can see that it does reflect over it, right? But why does it not continue? If you follow my cursor here, why does it not continue to curve like this, right? Why does it not snake all the way up? Well, it actually does, right? But we're trying to restrict this specifically such that it's a function. So let's go back here and kind of take a look at this, right? So why is this so small? The inverse exists when we flip x and the y values, right? So in other words, if sine goes up and down from left to right, then this is going to go left and right, as we go up and down, right? It's kind of the opposite idea. Now, if we did this, look at this graph here, right? Remember what it means to be a function. We have to be able to pass the vertical line test. So our initial sine graph does pass the vertical line test because no matter where we draw a line up and down, we're only going to get one value for x, right? As we plug in one x value, we're only going to pop out one y value, right? We need one input for every output. Now, what happens if I put in a 0 for sine of negative or inverse sine, right? If I plug in a 0 here, you'll notice that there's tons of points that this hits, right? It'll actually have an infinite number of points, and that can't exist as a function, right? So the problem is that inverse sine of x isn't a function the way it would naturally occur. So we have to restrict the range of this, right? We're going to pick a point from right here. You can see this point that I'm circling. We're going to pick that point to here, right? In other words, we're going to specifically choose on our graph. Let's just use red. It doesn't really matter. We're going to pick the point from here, and we're going to go up through to here, right? That's the point we're going to pick because we have to restrict the range such that it doesn't repeat. Because if the range repeats, then we're going to not have a function anymore, right? So you notice that we're picking the values between negative pi over 2 all the way up to pi over 2, right? And that's what this reflects here. If we go back to Desmos and we just kind of get rid of this other stuff, right? You'll notice that it goes from negative pi over 2 all the way up to pi over 2, right? So that's the range that we have to restrict this to. Now, let's take that concept and let's do it for cosine, and then let's do it for tangent, right? So let's post cosine, and then we'll look at what cosine, inverse cosine looks like, right? Or arc cosine, it's the same thing. You'll notice that here it's kind of the same idea, right? If we repost this, but it's shifted, right? And the reason why it's shifted is because cosine is just a little bit different. If we were to draw a horizontal line, right, there are certain points where it would work, right? But there's other points where it wouldn't. And that's kind of what we're talking about here, right? You notice here we're going from 0, because we're looking at our y values now, right? We're going from 0 all the way to pi. So we're actually restricting cosine from 0 to pi. Okay? So remember, sine, we restricted specifically from negative pi over 2 to pi over 2. And cosine, we are restricting from 0 here all the way up to pi. Now, tangent is actually going to look a lot like, if we do tangent here, this is our tangent graph, right? Our inverse of tangent looks like this, right? When we flip our y and our x values. Now, you'll notice that tangent inverse actually kind of passes this test pretty well, right? It's not as big a deal, but it's actually naturally restricted, which is different than the other ones. But you'll notice that the inverse of tan is actually naturally restricted such that we never hit pi over 2 for our y value, right? We never get as high as pi over 2, and we never get as low as negative pi over 2, but that is the natural restriction, right? The natural restriction is from negative pi over 2 all the way up to pi over 2, but we never actually touch those. So the inverse of sine and the inverse of tangent actually are very similar, right? It's just the only difference is that in sine, we do touch all the way down there and all the way up here, and in tangent, we don't. Okay, so you're probably asking yourself, like, well, there's probably two questions you're asking. Why do we choose that piece? Is a good first question. Maybe you noticed that, maybe you didn't, right? That's fine. So when we look at the inverse of sine, why didn't we take, and follow my cursor here, why didn't we take this point? Wouldn't that also work? And the answer is, yes, it would actually work, right? If we took this point and went from here to here, it would also work, right? If we took this point from here to here, it would also work, right? Because we're not gonna fail the vertical line test in either of those. But we are specifically picking the one that's gonna be easiest for us to use. And that's literally it. Like, could we use the other ones? Yes, but these are easier, right? And they need to follow a certain amount of rules, and all of these follow the rules, but the one we chose was the easiest. All right. Think of it as like we use in math, we use base 10, right? Everything that we do in math, we use base 10. Could we use base 7? We absolutely could. Would it change the logic of the math that we use? No, it wouldn't. Like the math would still work. It would just work differently, right? The same way that all of our trigonometric functions and our inverse trigs functions would work differently if we pick different places. It could happen, it could work, and it would work, but it's going to make your life harder, right? So that's why we picked these. Just if you were curious as to why, like, why this piece, okay? So that's why. Now, the other question is, what does understanding this restriction actually do for us, right? Like, why do we care that it's restricted? Well, that's because when we go to use our calculator, you're going to notice that the calculator naturally assumes that this is what we're doing, right? And I'm going to prove that to you here, okay? So let's go up here and let's talk about evaluating inverse trig functions. So let's look at if we evaluate inverse sine of 1/2, right? Let's put that into a calculator. So let's do inverse sine of 1/2, and we get 30 degrees, right? We already knew that though, right? Because what inverse sine is asking us is what angle has a sine of 1/2? Well, where sine is 1/2, we know that angle is 30 degrees, right? Sine of 30 is 1/2, right? We've looked at that on the unit circle. So we know that sine of 30 is 1/2. The question is, isn't there also another angle where sine is positive and sine is 1/2? Isn't this also true, right? So in other words, if we have sine of 30, isn't the other sine, that's where sine is positive here, with a reference angle of 30, isn't this also positive 1/2? And the answer is it is, actually, right? This here would be, what, 150 degrees, right? So it'd be 30, from the x-axis here, and this is 180, right? So 30 from 180 is 150. So if we have our theta here of 30, this theta is 150, and both of them are angles that produce a sine of 1/2. So when we type this into our calculator, why does it not say sine of, or inverse sine of 1/2 is 150? Why does it only say 30? Well, what did we just talk about? We just talked about the fact that we have to restrict this, right? In other words, if sine is from negative pi over 2 to pi over 2, it's actually only going to exist in this quadrant, right? I'm trying to draw this real quick, but it's not going to look very good, right? If I have my quadrants, right? If I have negative pi over 2, which is down here, sine exists only, I'll use red, sine exists only in this area, right? This is the only place that sine can exist. And remember, this other angle exists over here, which is not in our restricted range. And remember, we had to restrict the range. So if we evaluate this, right, if we actually, I don't know what just happened. Okay, if we evaluate this, right, of inverse sine of 1/2, our calculator will only give us 30 because that's the only one that fits within our restricted range, right? And that's good. That actually helps us, right? Because we only want the ones in the restricted range. So let's think about this again, okay? But let's think about like why it would exist for cosine, right? So for cosine, if we use our calculator for cosine, cosine is only going to exist between 0 and pi, right? So cosine is only here, right? But let's think about how cosine would work, right? If I had cosine of 30 degrees, that's where x is positive. That could exist here, and it could exist here, right? Both of these thetas would work. But this one doesn't, because it's not part of our restricted range, right? And you'll see this as you go, right? But I was just kind of like explaining why this works the way that it does. It's actually good, because for the most part, when we evaluate the angle, we only want the angle that exists within the function that we're allowed to use. So this is, our calculator giving us 30 is helpful in most situations, all right? Now I'm going to show you the exact situation in which it's not, right? But it's more of an understanding of what the inverse sine is actually telling us, right? The inverse sine is evaluating the angle. We have to determine if that angle is the only one we actually need, which in most situations it is, okay? All right, so let's define all angles with a given trig function. Okay, so we're going to find all angles theta whose cosine is 0.57, right? In other words, if we were just going to like rewrite this as a problem, right, we would just write this as cosine theta equals, if you want to use 0.57, if you want to kind of understand what this is, it's just 57 over 100, right? So this kind of looks like anything that you're used to seeing, right? And what we would do is we would take the inverse cosine, I don't know why I put the negative over there, we would put the inverse cosine of both sides, right, and we'd solve. So that's kind of what we did here, right? I accidentally erased that line, I didn't mean to. All right, so if we look at this function here, right, cosine of theta equals 0.57, we take the inverse of both sides, and we get the inverse cosine of 0.57 equals theta. So let's just go and do that. Inverse cosine of 0.57, and that gives us 55.24. Okay, which is what we got here, 55.25 rounded. All right. Because your calculator is only going to restrict this to quadrant 1 and quadrant 2, right? That's what we just talked about. 55.25 is not the only possible answer for this, right? Technically speaking, cosine can exist down in quadrant 4 as well and still be positive, but it's also true that it doesn't fall within our restricted range. So that's what this is saying here, right? Because your calculator is going to restrict this to quadrant 1 and quadrant 2, because that's what it thinks cosine has to be restricted to, right? That's quadrant 1 is quadrant 1 is because that's where theta is positive, right? If it restricts it to quadrant 1 and quadrant 2, we got an answer for theta that's positive, which means it's going to choose the one in quadrant 1, right? That makes sense. So we need to manually find all the other possibilities. Now, we just kind of talked about that, right? We said that when we have a cosine function, right, if we have, give me this. All right, when we have a cosine function, remember that it's positive, right? If theta is positive for cosine, which is our x value, it's also positive here, right? It's positive in both these situations, but remember we're restricted to up here, so then this becomes the only possible answer, right? That's kind of the idea of what we're talking about here. But we need to know all the possible angles that could exist, right? Not just the one that we're evaluating at the specific inverse sign of this, right? Not just within our given function. So if theta for cosine is positive in quadrant 1 and quadrant 4, we can use reference angles to find the other answer. In other words, if theta is 0.5525, right, it's also 0.5525 here, but it's negative, right? In other words, this is still positive. This theta being negative still produces a positive value for cosine, right? Because our cosine is attached to our x value. So yeah, in other words, like if this point here was like 1, right, or like 1 comma 4 or something, like it doesn't really matter, right? Or this would be 1 0, but if this point was like 1 comma 4, this would still be 1 comma negative 4, right? And cosine would still be positive because it's tied to our x value, right? So when we talk about this, right, because theta repeats every 360 degrees, we can define each cycle as 55.25 plus k times 360 degrees, right? So in other words, what this is saying is if we have a unit circle, right, and we know that theta is this here, right, it is this distance, right, but it's also it's gonna continuously repeat, right? That's gonna repeat infinitely. So yes, it's this distance here, but it's also this distance here, right? And it's also this distance and this distance. And you see how we keep going around and around and around, right? So every time we can get our theta and we can add 360 degrees to our theta, and that'll give us the same answer, right? So if we rewrite our formula as this 55.25, which was the answer we got, plus k times 360, k is just the total number of extra revolutions, right? So k represents the number of each additional full cycle. So if we go all the way around an extra time, it's going to be 55.25 plus 360, right? If we go around twice, or 2 extra times, it's going to be 55.25 plus 2 times 360, right? Which is what the k means. It's just how many times. Now, the other thing we have to consider is this isn't the only final answer, right? It's not just this, right? This is one of our answers. But remember, the problem is that we also exist over here, right? So in other words, this half of it also works, right? So negative 55.25 is the same thing as 304.75 degrees, right? If you take 360 and subtract 55.25, you get 304.75. So because negative 55.25 is the same as 0.75, we can define this part as well, right? So this one was 55.25 plus k times 360. We can also define this as 304 plus k times 360. Because if it goes to here, it can also go another revolution and then another revolution. And both of these will give us positive values for our cosine. So we have to account for both. So both of these answers are correct. So it's not only the 55.25 plus k times 360, it's also our 304 plus k times 360. So both of these answers are true. And remember, this all stems from the idea that we have to be careful when we're using our calculator if we're trying to find all possible angles, right? If we're just using it to evaluate what the actual angle is, we don't have to worry about this. But if we're actually trying to figure out what all possible angles are, then we do, okay? So let's go ahead and work on solving trig equations, right? Now, I did want to provide one little caveat here real quick, right? You'll notice that sine and cosine have 360 degree cycles and tan has a 180 degree cycle. So if we use this formula before, the k times 360, if we're using tangent, it's going to be k times 180, right? Because each cycle is only 180 degrees, not 360. So just keep that in mind, right? If you do sine or cosine, this k times 360 will work. If you do tangent, it has to be k times 180. All right. So, like I said, let's go ahead and solve trig equations. And the thing about solving trig equations is a lot of people overcomplicate this. It really is as simple as doing exactly what you would do if the function itself, or the trigonometric part of the equation, if you just think of that as like an x or a variable or something like that, it really makes the problems a little bit easier. And I'll show you what I mean, okay? So you can apply a lot of the same algebraic operations you could use before. Okay, so just to highlight a few, I know that if I have if I have the inverse of a function, right? If I have the inverse of a function, it just equals that function, right? So in other words, inverse cosine of x is just going to equal x, right? And we've used that a bunch already, right? If we go back here, right, if we're taking the inverse sine of 1/2, what we actually did is from this step, right, when we have this function, we have to take the inverse sine of both sides. That's how we get theta by itself, right? If you want to like kind of see that written out, I'll show you here real quick. You can skip this if you want. But like if we have cosine of, let's just say we have cosine of theta equals, I don't know, 2/3. It doesn't really matter what the number is, right? To find what theta is, what we're doing is we're taking the inverse cosine. I don't know why I keep doing that. We're taking the inverse cosine, right, of the cosine, right, of theta. This is what we're doing, right? And then these cancel. So it leaves us with theta. And then because we took the inverse cosine on this side, we have to take the inverse cosine of this side, right? And that's why our problems just look like this when all is said and done, because we're actually using this to negate, right? It's kind of like, if you see it over here, it's kind of what I was talking about. If we have 2x over 2, that's the same as x. Because these are multiplicative inverses, they cancel out. These are function inverses, so the function inverses cancel out, right? It's just another way of looking at that. Okay, so we can do that, right? We can always take the inverse of a trigonometric function to get rid of the actual trigonometric function, right? That's ratio. That's what we do, right? So we can do that. The other thing we can do is we can just add them. So if we have cosine of x, right? So if we go over here, if we have cosine of x plus cosine of x, that's 2 cosine of x's, right? If this was like a x plus x, we would just say we have 2x, right? Well, cosine of x plus cosine of x equals 2 times cosine of x. And then we can do the same thing with like the square root, right? So in other words, I'll just kind of do it over here. If we have cosine squared theta, and we know that equals like 4 or something like this, it doesn't matter, right? We can take plus or minus the square root of both sides, right? And then we know that cosine theta equals plus or minus 2, right? And then we have to evaluate whether or not it's plus or minus based on what quadrant we're in and all that stuff. Okay. Cool. So like I said, we can do a lot of the things we could do algebraically. We can do the exact same things with these trigonometric ratios. All right. So find all angles theta for 6 sine theta equals 3 sine theta plus 2. So let's go and actually use what we just learned to solve a problem here. So the first thing we're going to do is, well, if we look at this, let's just pretend, like I said, let's pretend like these sine thetas, let's just replace them with x temporarily. So if I had 6x equals 3x plus 2, right? How would you solve this? Well, you'd subtract 3x from both sides, right? And you'd get 3x equals 2, and then you'd divide by 3, right? And you'd get x equals 2/3. Well, that's literally what we're going to do, okay? So if we go into our problem here, let's look at it, right? So we have 6 sine theta equals 3 sine theta plus 2. Well, let's subtract 3 sine theta from both sides, and that's going to leave us with 3 sine theta equals 2, right? Divide by 3, and we get sine theta equals 2/3. Now, once we get here, right, in order to get what theta is, we have to take the inverse sine of both sides. So if we take the inverse sine of sine, that cancels out. And then the inverse sine of 2/3 is, well, it's the inverse sine of 2/3, right? That's what we can plug into our calculator. So if you go here, inverse sine of 2/3, right, we get 41.8, right? Which if we go back here, oh, they're using radians. That's fine. That's easy, easy fix. Radians. Okay. So if we do the same thing, right, 0.729, so 0.73, right? So 0.73 radians. Now, this is our answer, right? This is theta. So in other words, theta is 0.73 radians. We know this, right? Now the question is, for what angles is this true, right? So in other words, we have 0.73 radians, but we also have to think, right? Think about what sine of 2/3 is, right? So sine of 2/3, if we think about this, right? Well, okay. So let's think about these numbers real quick, because this is a little bit counterintuitive because we haven't really done this so far. But if we think of just the top quadrant, right? This is 0, right? This is pi over 2, and this is pi, right? These are numbers, right? This is 3.14, right? And this is 3.14 divided by 2, right? So you don't need to like memorize these numbers, but you can kind of figure out what they would be, right? So 3.14 divided by 2, just to kind of get a general feel, is 1.57, right? So in other words, from 0 all the way to 1.57 for like this distance here, this distance exists in quadrant 1, right? So we got 0.73 radians. 0.73 is going to be, about half, right? Something like this, right? This would be 0.73, right? And we're talking about sine, right? Well, where else is sine positive? It would be positive where this is 0.73 this way, right? So what we do is we know that, okay, this distance here, this theta, right? If we refer to that as theta has to exist, right? Also, where we take our pi value, but we subtract 0.73, right? So in other words, 3.14, and you can just put the pi symbol into your calculator, right? Minus 0.73, and that's going to give you 2.41, and this is going to be your radian measure as well, right? So in other words, the sine of 0.73, right? So sine of 0.73 is also true. Like the same angle exists at sine of 2.41, but remember our calculator isn't going to give us this because this exists in quadrant 2, and the inverse sine can't exist in quadrant 2. So we found both of the answers, right? And now we just need to find all angles. Well, all angles can exist when it rotates all the way around a bunch of times, right? Which is why if we look over here, what we did is we said, okay, we found the 2.41, right? Therefore, pi equals 0.73, or sorry, theta equals 0.73 plus k times 2 pi, right? 2 pi and 360, it's the same concept, right? We can use 2 pi because we're using radians. And then also our 2.41, we can also add the k plus, or k times 2 pi as well. And like again, what all that's saying is that if we have our 0.73, right, which is like this angle here, right, this also exists, like we exist here, we also exist here, right, and that would be where k would equal 1, and then we can keep going again, and that's where k equals 2, and this is true, right? All of these angles are going to look exactly the same, but they're going to be different values, so we have to account for all of those values. So the answer to the question, right, the question is find all angles. Well, the angles are 0.73 plus k times 2 pi and 2.41 plus k times 2 pi. These are all of the possible angles here. All right. Well, cool. So that's it, really. That's what we're going to talk about today. I know a lot of this is pretty dense as far as the difference between when you use inverse sine, like when you can use the value the calculator gives you and when you can't. And the quickest way I could sum it up is, and this is honestly the easiest way to look at it, is when you are looking at a problem that literally looks exactly like this. When you are typing inverse sine of something and you just want a value, your answer will just be the answer the calculator gives you. If you need to know all of the possible angles that could exist, right, then you have to search by using the unit circle, find the reference angle, and do all the stuff that we did like on this half of the notes, right? That's not going to come up very often, right? It's not something that you really need to know. I mean, it's something you need to know, but you're going to run into this more often. So I don't want you to think that every time you type this into your calculator, you have to worry that there's a bunch more answers that you could find, right? Because in theory there is, but you're probably not going to need them for the problem, okay? But if you did, this is how you would find those angles. Here's how you can find all the possible angles for any, or all the possible angles for a certain theta, right? Or a certain looking angle here. All right, that's it. So first we defined and evaluated trigonometric functions. We did that by actually looking at a graph, defining what a function is, and then understanding that we have to restrict the range of our trigonometric functions specifically. And then to solve equations using the inverse trig functions, we not only learned how our calculator does this and why it does this, but we learned if we need to find all of the other angles that exist, we learned how we can evaluate it based on the idea that our angles are going to repeat infinitely, right? All right, well, that's it. I will see you in 8.2, and have a good rest of your day.